Hello and welcome. What did one stoplight say to the other stoplight? Turn around, I'm going to change. In this video, we're going to look at an application of the derivative called Newton's method. Let's check it out. So as it says, Newton's method is a way of approximating solutions to f of x equals 0 by using the tangent line of f. And when we think tangent line, we're thinking derivatives. To get an understanding of what Newton's method looks like in a graph, let's take the graph of some function that has an x-intercept. So there's the x-intercept, it's where the graph hits the x-axis. And our goal is going to be to find the x value where f of x equals 0. In other words, find the x-intercept. Well, what Newton's method says is start with some x value, we'll call that x1, and plug in x1 into the function. So plug it into the function. There's where the dot is at that x value. Then it says find the tangent line to that function. So there's the tangent line of that function at x1. And see where the tangent line intersects the x-axis, which would be right about here at x2. Now that's fairly straightforward to find, and we're going to do that algebraically. Then it says repeat this process. For this new x value, x2, go up to the function, draw a tangent line through that point, and see where that tangent line hits the x-axis. We'll call that x3. You can keep repeating and repeating this process over and over again, and you'll notice how these x values, this sequence of x values, gets closer and closer to the x-intercept of our function. So this is really cool. It's a method of getting closer and closer to the x-intercept, even when you can't find the x-intercept directly through algebra. So you'd plug in x equals 3 and repeat the process. So in words, here's what Newton's method would look like. Number 1, guess a first approximation to the solution of the equation f of x equals 0. This will be some kind of x value. And then number 2, use the first approximation. Again, the first approximation is x sub 1 to get a second. And then use the second approximation, that's x2, to get a third, which is x3, and so on. And the way you're going to get from one x value to another is using this formula. So x sub n plus 1 equals x sub n minus f of x sub n all over, or over f prime of x sub n. Why is this formula the way it is? Well, we're going to derive it and explain why. Let's come on over to the notes. I think you got a peek of my joke file. Okay, so we'll take a look at why this Newton's method is the way it is, why this formula is to get the next x value is the way it is. Do that right here. Well, first off, for that first x value, x sub 1, if we draw the tangent line, or if we find the tangent line at x sub 1, that is just the linearization of the function at x equals 1. If you remember from a prior section, we talked about the linearization of a function at an x value, and all that was an equation in function notation for the tangent line. So let's write up what we found in that packet. We found that the linearization could be written as f of, and we used a before, but here we're just going to jump into x sub 1 because that's the x value that we're at. F of x sub 1 plus f prime of x sub 1 times x minus x sub 1. So this is the equation or the function of the tangent line. This is a function that represents that tangent line at x equals 1, x sub 1. So let's go ahead and find the x-intercept of that tangent line. We want to follow that tangent line and figure out where is that tangent line going to give you a y value of 0. which is where the x-intercept of the tangent line is. That'll help us find x sub 2, x2. So we get the x-intercept by setting the y value equal to 0. In other words, you're going to just set the function equal to 0, L of x equal to 0. So we have f of x sub 1 plus f prime of x sub 1 times x minus x sub 1 equals 0. If we can figure out the x value, where that's true, then we'll have figured out x2. And we can do that. We can take the f of x sub 1, subtract it to the right, divide by the f prime of x sub 1. That'll look something like this. And then as a last step, add the x sub 1 over. So you can see that we arrived at basically this formula. The only thing is this formula is written in terms of any x value that you're at. So you could be at x sub 5 and you want to find x sub 6, x sub 5 plus 1, which would be x sub 6. So this keeps happening for every x value because the process is exactly the same. Once you have a new x value, you do the same thing. You find the equation of the tangent line at that x value, figure out where it's equal to 0, and that's x sub 3. And this is exactly how you're going to find where that next x value is equal to 0. So just to point out though, this x here is x sub 2. And then you just repeat. To find x sub 3, it's the same formula but just with x sub 2's. So let's use Newton's method for example 1 to estimate the positive solution of the equation x squared minus 2 equals 0. We're going to start with x sub 1 equals 1 and then find x sub 4. So we're going to go 4 iterations through Newton's method. Well, our function here, the one that we're trying to find the x-intercept of, is x squared minus 2. So this is our function, f of x, x squared minus 2. I'm going to write that over here. F of x equals x squared minus 2. Now we're going to need the derivative of that function to apply this Newton's method, and that's going to be 2x. And we're going to start with x sub 1 equals 1. That's our starting x value. We need that first starting x value in order to get the next one. And we'll get the next one using the formula that we came up with. So this will be x sub 1 minus f of x sub 1 over f prime of x sub 1. When I'm writing out Newton's method, sometimes I think you're layering on the function and then the derivative of that function. So it's x sub 1 and then minus f of x sub 1 and then over f prime of x sub 1. So it's like you're constantly layering on things on. It just is a little mnemonic to help me out, help me remember this. So then we have x sub 1 is 1. We'll put the 1 in all these places. We have 1 minus f of 1 is 1 squared minus 2. F prime of 1 is 2 times 1. So we get 3 over 2 when we evaluate that. This is, actually let me break this out a little bit more. This is 1 minus negative 1 over 2, which gives you 3 over 2, which I'm going to point out in a slightly different color is 1.5. 1.5. Okay, so there's x2. Let's plug in x2 into the formula to get x3. x3 will be x2 minus f of x2 over f prime of x2. I'm going to use the fractional version of it. Even though the decimal is exact, in this case I'm just going to use the fractional version because some of the future fractions won't be exact. So we have 3 halves minus f of 3 halves over f prime of 3 halves, which, long story short, gives you 17 over 12, which is approximately 1.41667. Now we can find x sub 4. That'll be x3 minus f of x3 over f prime of x3. So that's 17/12 minus f of 17/12 over f prime of 17/12. This ends up giving you a fraction 577 over 408, which is approximately equal to 1.41422. Okay, so there's x4. Here's the exact version of x4. The decimal approximation is this one, the 1.41422. You can just look to see what the problem is asking for. If it just says find x4, probably either one will be fine. If it says find the exact x4, then it's the fraction. If it says find an approximation out to 5 decimal places, that would be what we have written here. Now, one thing I wanted to mention is that we can actually figure out what value satisfies this equation right here, what value of x satisfies this equation, by just solving it. So let's do that, just so we can compare what Newton's method got to what the actual solutions of that equation are. So I'll put a little note. X squared minus 2 equals 0 will lead you to x equals plus or minus root 2, which, if you calculate the square root of 2, you end up getting something like approximately 1.41414. So the true 0 is, this is the true 0. Is the square root of 2, or the, that's the decimal version of the true 0. And notice that the x4 that we got in just 4 iterations of Newton's method, we got the first, let's see, 1, 2, 3, 4 decimal places. First 4 decimal places exactly the same. So Newton's method can converge to the correct solution to the equation very, very quickly. Now, of course, it depends on the kind of function you have. It depends on the properties of the function. And in fact, one of the downsides of Newton's method is it doesn't find every 0. It just finds a 0 that's close by. 2 more things I wanted to mention that are on page 2 of packet 12. The first is how best to use your scientific calculator for Newton's method. For this, you'll need to understand how to use the ANS button, which refers to the current answer on your calculator. Now, I've written out some instructions about how to use the ANS button. If you have any questions about this while you try it out, please let me know. The second note I wanted to mention was that if you're using Newton's method with a trig function, so if there's a function that has, if your f of x is a trig function and you're trying to figure out where is it equal to 0, then be sure that your calculator is in radians mode. So for example, if you had to estimate the solutions of sine x equals x squared, the first thing you would do is subtract the x squared over to the left, make your function sine x minus x squared, and then make sure your calculator is in radians mode before you follow the instructions about how to use your scientific calculator for Newton's method. So thanks for watching, and see you next time.